So in this video we're going to solve a differential equation using separation of variables in the case where we have an initial value problem. So in the previous two examples that we did when we finished, we found the general solution, which meant that we had the constant of integration. So the idea is if we're given additional information about the differential equation, and so here we're being told that when x is equal to 3, y is equal to 4, so we're being given the ordered pair xy equals 3, 4, then receiving this additional information makes this into an initial value problem. We're given a value which lets us then solve for the constant of integration. And when we solve for the constant of integration, we're actually finding a particular solution. So here I could actually say find the particular solution for the differential equation given these conditions where when we input 3, the output y has to be equal to 4. So here I have y prime equals the opposite of x over y, but y prime is just dy dx. So if we multiply both sides by dx, we get dy equals the opposite of x over y times dx. And if we multiply both sides by y, we get y dy equals the opposite of x dx. And now we've separated variables because dy is on the left and all of the y stuff is with the dy. Dx is on the right. All of the x stuff is with the dx. And the next step is to integrate. The negative is a constant, so it can be factored out in front of the integral. So I can get the opposite of the integral of x dx. And now we just integrate. So integrating, and we need to add on that constant of integration that we get by integrating both sides. So integrating the left-hand side, we get 1/2 y squared. And then over here we get minus 1/2 x squared plus that constant of integration. If I add the minus 1/2 x squared to both sides, I get 1/2 of y squared plus 1/2 of x squared equals the constant of integration. And if we multiply through by 2, we get twice c on the right hand side, and we get a y squared plus x squared, or x squared plus y squared, because the order of addition doesn't matter. And if we have 2 times a constant, that's just another constant. So I can rewrite twice c as a constant. And what I want to recognize here is this is just if c is greater than 0. For any c greater than 0, this is just a circle. X squared plus y squared equals r squared is the equation of a generic circle. So if I rewrite c as the square root of c squared, I have circles of radius square root of c, but the square root of c is just, so if I have twice c1 equals c2, and this is really my c sub 2 here, the square root of c sub 2 is just some constant as long as c is positive. So I can actually rewrite this as, if c is greater than 0, I could rewrite this as c squared. So hey, this is the circle, the family of all circles of radius c. That's assuming that c is greater than or equal to 0. If c is negative, then we don't have circles. So this is the general solution, and it would be perfectly okay to write that as a c squared. I don't need to though. So this is the general solution because it has the constant of integration in it. But when we're given some initial conditions, for x and y, we can actually then solve for that constant of integration. So in this case it says, hey, we have x squared plus y squared equals c, but we know that x is 3 and y is 4, so when we plug this in, I get 3 squared plus 4 squared equals c, and this is going to turn out to be 25 equals c, or 5 squared is equal to c. So then if I replace the c with 5 squared in the original, I get a particular solution, x squared plus y squared equals 5 squared. We get a particular solution, or in this case, we get a particular or specific circle, the circle centered at the origin whose radius is 5.